Okay, okay. Going to do is some very important derivations, including a graph. Okay, so please pay attention how those things are derived. Very easy. It's all in the same way, and that is yeah, we have learned. Yes. Oh. Radioactive decay. Law of radioactive decay. This is an important derivation. Yes. What is law of radioactive decay says? It says that in a large sample of nuclei, the probability of decay, okay, the probability of decay determine the fraction of the nuclei that will decay each second. That means assume that you have got say 100 undecayed or original atoms, for example uranium atoms at the moment. After some time, some of them have decayed. This is when T is equal to 0 in the beginning of you making that sample. After some time, some of them have decayed. Say after time T is equal to T, some of them decayed and you have got only 80 undecayed uranium atoms. Now this 100 in the beginning what we have is represented by the letter N0, okay, in the beginning. At the moment what you have, that is a N, okay, in the beginning when time was 0, you had N0 number of total atoms, of which 20 have decayed and became some other element. So now at the moment you have got 80, which is represented by En. And how much have decayed? Let the difference between them, that means 20, that is Dn. Okay, how many have decayed? In this example, it is 20. In what time? In a time dt. Okay, so the number of radioactive nuclei decaying in a certain time. Let Dn be the small if you take a small time interval, in a small time interval dt, how many nuclei decayed? Let that be Dn. And the law says that the number of nuclei decaying in a second, okay, decaying in a certain time, that means dn by dt. What is this one? Number of radioactive nuclei decaying in certain time, in certain time or in a small time. Number of radioactive nuclei. This is also called the rate of decay. Rate of decay. This rate of decay, according to the law, this rate of decay is proportional to the present number of atoms. All right. So that means the law says that the rate of decay, dn by dt, how many decaying? It is proportional to the number of the atoms present at that time. Okay, so now this proportionality sign can be replaced by a constant, and that constant is our decay constant, lambda into n. In fact, there is a negative sign here. What does the negative sign shows? This negative sign shows that as time increases, what happens to the number dn or n as time increases? That means after some time, for example, say after t is equal to say t1, how many and how many will be that time n will be less than this one, maybe 60 for example. Okay, at that time let n be 60. So as time, but here the time has increased. When time increased, what happened to n? N was 80, n decreases. Okay, so as time increases, n number of undecayed atoms decreases. That is why since one increases, the other decreases. That's why you have got a negative sign. So dn by dt is equal to negative of lambda n. This is radioactive. This is the rate of decay or the decay equation. Now from this you can make a normal equation after integrating. How can we write the normal equation? You rearrange this one, you bring n's on one side, take dt to the other side. So remember, listen carefully to this way of derivation. They will ask you this derivation. Okay, so what you do, you rearrange dn by n is equal to negative of lambda dt. Okay, now what you have to do, integrating. Have you learned integration? Huh? Okay, so now you can help with the other steps. Integrating both sides. What do you get? Integral of, okay, 0. Let's say in the beginning you had n naught, now you have n. Okay, n naught to n. dn by n is equal to minus lambda. Lambda is a constant, so you can take the constant out of integration, 0 to t. Okay, in dt. So here it is 0 to t and it is dt. Here it is also n and it is dn. Now what is the integral of dn by n? Integral of dn by n. Integral of dn by n. Sanjita. Mashar. Natural log of n. Integral dn by n, that means integral 1 by n dn, okay, is equal to natural log of n. This is the integration rule. So natural log of n between the limits n naught to n is equal to negative of lambda. What is integral of dt? Mashar? Integral of dt? Simplest. Sanjita? Farheen? Is t. What is this one? That means integral of dt means when you add up small time intervals. If this is one time interval, this is another time interval, this is another time interval. If this is 0, likewise, you have so many time intervals up to t. What is the sum of all these intervals? 0 to t is t. Integral dt, that means summing up the tiny time intervals, is equal to the total time. Okay, so here integral 0 to t dt will be t between the limits 0 to t. Now what to do, Mashar? Now you put in the values. So first what you have to do, you have to eat, that means this is the variable. In the place of this, you put this variable, minus in the place of this, you put this variable. Okay, that's the next step. So in this is log n. When you put n there, you will again get log n minus. Now in the place of this variable, when you put n naught, you get n naught. is equal to negative of lambda minus, in the place of t you put 0, this one. So rearranging, what do you get? ln n minus ln n naught is equal to negative lambda t. Now use a rule of logarithmics, subtraction of two logarithmic with the same base. How can you combine this? ln n by n naught. All right, memorize these steps using different rules. All these are integral rules. This is logarithmic rules. ln n minus ln n naught is equal to ln n by n naught. That means log a minus log b is equal to log a by b. This is how you expand logarithmic. All right. So this is equal to negative of lambda t. Now look here. I have this natural log. I have to remove this one. How can I remove this natural log?
E.
Yes. So taking exponents both sides. That means here also you are putting e to the base of this is equal to e to the base of this. So what did we get? Okay, e ln n by n naught is equal to e negative lambda t. Okay, now you know that e and ln, they are inverse, or whenever you take an exponent of a logarithmic function, this one disappears. So this whole thing will become n by n naught is equal to e to the power negative lambda t. Now this is removed. Rearranging this, what do you get? Cross multiply. En is equal to, what is this? Number of undecayed atoms at any instant is equal to now n naught e to the power negative lambda t. Very, very important equation. This will help you to find the number at any time after a certain time t, if you know the decay constant. How can you find the decay constant? This decay constant can be found by ln 2 by t half. So using this, you find a decay constant. Then at a certain time, either you find n naught or en. All right. Now, what kind of function is this? You're familiar with this function. Something e naught e to the power negative t, negative something. Where have you learned a function similar to this? Ashar, last unit you learned? Recall.
There were three equations.
What were they?
One for current time, and other is voltage time and charge and time.
Yes, they were for discharging curves of a capacitor. Okay, discharging curves. See, look here. So it's an exponential function, negative exponential function, and their graph will be what? If you plot a graph between n and t, it graph is a negative exponential. That means exponential growth, decay curve. Okay, so the graph of n against t will be an exponential decay curve, just like capacitor discharging graphs. Okay, so what all you have learned in the capacitor discharging calculation, you can now apply because they are very similar. Have you understood this derivation?
Yes.
Okay, so all these things you can, I want you to take down this derivation at the moment and memorize as you write. So what does law of radioactive decay say? Law of radioactive decay says that the rate of decay, number of nuclei decaying in certain time is proportional to the number of undecayed, where n is the number of undecayed nuclei at that moment. Yes, yes. Okay. So this is the number of undecayed nuclei at that moment. So the number at any time is proportional to the number at the rate of decay is proportional to the number present at that time. So using this law of decay, we are getting an exponential equation. So please take this derivation down, because from this only we are going to get the other derivations. Memorize as you write or understand as you write. Here you write n naught is the total number when t is equal to 0. That means initial number. Okay? This is okay? Are you done? Sanjita, done?
Yes, miss.
All right. Yes, Farheen, done?
Yes, miss.
Now, using this equation, we can derive two more. That is, we have learned the relation between lambda and half-life. Okay, we know that equation. Now, what is the derivation for that? How that equation is obtained? We know that when or after one half-life, that means when, okay, in the beginning, you have n naught. Now, say you have n after one half-life. T half is a half-life. This n will be, or okay, for example, let this be n naught. Let this be n naught. After one half-life, the number will be half of this one. Okay, this is when t is equal to 0. This is when t is equal to one half-life. So when t is equal to one half-life, the number of undecayed atoms will be half of this one. Okay, so we know this already. So now let us write the equation. N is equal to n naught e to the power minus lambda t. So after one half life, what will be the present number? After one half life, the present number is n naught divided by 2. Okay, is equal to n naught e to the power negative lambda. At that time, what is the time? Time is t half. Understood how we got this one? This is the equation that we know. After one half life, n will be n naught by 2 and t will be t half. Okay, after one half life. So putting that values in this equation, you get this one. Now what can we do? You can cancel n naught. What do you get? Half is equal to e to the power negative lambda t. Now what do we want to do? We have to remove this exponent. We know that log, natural log and e are opposite. So what do we do? Taking natural log on both sides. Ln half is equal to ln e to the power negative lambda t. No, t will be t half. Why didn't you tell me that? T half. Okay. Now simplify further. So now how to expand this one? How to expand this? Ln. Okay, the opposite of what we did last time. I told you ln a minus ln b is equal to ln a by b. Now you have to do the opposite. We have ln a by b, ln 1 by 2. So how to expand? ln 1 minus ln 2.
Yes.
Okay, ln 1 minus ln 2 is equal to, now I told you log and exponents are opposite. So both of them gets removed. What is left is minus lambda t half. Okay. Now what is the value of ln1? 0. ln1 is 0 minus ln2 is equal to negative lambda t half. That means minus ln2 is equal to minus this one. So you can cancel these minuses. These minuses can be cancelled. So what is left? ln2 is equal to product of lambda into t half. Therefore, lambda or t half is equal to ln2 by the other one. Okay. This is how we got that important, very, very useful equation. This is the derivation. Okay. Understood?
Yes.
From this, what only we did, we assumed this one. After one half life, number will be n naught by 2, t will be t half. Simply put that in this equation and continue. So this also you take it down. Also, we learned n is equal to n naught e to the power minus lambda t. Now, we are going to learn another equation. Activity is equal to negative of dn by dt. Okay, negative of this one. So, what happens? A is equal to negative of dn by dt. So, this negative of this one Now dn by dt is equal to another negative of lambda. So there are two negatives. Therefore, activity is a positive number. Therefore, this is equal to lambda n. All right. So what do we get? A is equal to lambda n. And what is n? We already have an equation. N is equal to lambda into n naught e to the power negative lambda t. Now this lambda and n naught is taken as lambda into n naught is taken as activity in the beginning. So instead of this, if you write a naught, what do we get? A is equal to a naught e to the power negative lambda t. This is the equation between activity and activity in the beginning. This is also an exponential decay curve. So the graph of activity against time would be again decay curve. So please note that it will not become zero, but it will go close to this one for a long time, but it will take a long time for it to become a zero. That's a property of exponential decay curves. Okay. So we got A equals A naught e to the power minus lambda t. So depending on the question, only these four equations need to be applied in radioactivity for doing the calculations. Okay, there's one more equation after this. There's a logarithmic equation. Last derivation, which is logarithmic equation. Okay, logarithmic equation. It is again based on this. We know that n is equal to n naught e to the power negative lambda t. Now taking logarithmic, we are going to get a logarithmic equation for that. We did a similar one regarding capacitor also. So taking logarithms both sides. What is the purpose? Basically to get rid of this e. Okay. Now, so ln n is equal to ln. Now here you remember, tell me how is the expansion of this? ln
N naught minus L.
No.
Minus lambda t, because...
Wait. Ln n naught, here there is a multiplication, right? Here there is a multiplication. So it becomes plus ln e to the power negative lambda t. Okay. So now you can take, yes, now this is enough. Now, what is this ln and e? Opposite. So this gets cancelled. So it becomes ln n is equal to ln n naught minus lambda t. Now this is in the form of, you have to rearrange this in the form of y is equal to mx plus c. Okay, so here y is this one. Okay, y is this one. Here, which is the variable, here x is the variable, and the coefficient of x, m is the gradient. Okay, similarly here, what is the variable? ln n naught is a constant and the variable is t. So x is equal to t. T comes in the place of x. So you rearrange this one in this form. What do you get? Ln n is equal to m into the variable one. So the variable is t. So take that one first, negative lambda t plus ln n naught. Okay. So this is the equation. Now it is exactly in the form of y is equal to mx plus c, which is the equation for straight line graph. So since here what do you get? The coefficient of this is the gradient. Therefore, here m is equal to negative lambda. Okay, m is equal to negative lambda. That means the graph will be, its gradient will be a negative graph. It will be something like this. And the y-intercept mx plus c. C is equal to ln n naught. So here what do we have? Ln n versus time, and this y-intercept will be ln n naught. And this gradient, okay, this is one thing, ln en naught. And the gradient of this m will be negative of decay constant. So what is the use of this one? So once you know, therefore, the decay constant m is equal to negative of m. That means negative of the gradient. And the significance of this is that you, from the graph, you can find the lambda. Therefore, half-life could be easily found is equal to ln 2 by lambda. This is the use of this one. Understood? These four derivations are important. They could ask you in any way, either in the form of graph or calculations or directly derivation. Okay, there are a lot of questions in the textbook, index questions, and simultaneously start doing the past paper questions as well using this, and let me know if you have any doubt in any of these things. Now, in addition to this, you can also have another useful equation, derivation of which is not required. That is a way to find the half-life or the time or any other one. That is this one. Another important useful equation, number of atoms present at any time, nt, any time, is equal to initial number n naught into half, because using half-life, half to the power of 1 by half-life. Okay. So in any question related to half-life, or if half-life is given to you, how will you find the original number or initial number? For that, you can use this equation. Okay. The number at any time, n is equal to this one. Okay. This t is optional. Here also we could write in this n t, this t is optional. You could directly write n is equal to n naught half to the power 1 by half-life. This is not multiplication. This is to the exponent, to the power. Spontaneous nuclear process. Okay, spontaneous nuclear process. I told you we are going to study this topic in 3 parts. Number 1, introduction about nucleus, then spontaneous nuclear process, which is radioactivity, which you are done with. Now non-spontaneous or triggered nuclear process. Okay, triggered nuclear process, which is nuclear fission or nuclear fusion. Okay, so the difference between this is that in radioactivity, you don't have to do anything. It happens from an unstable nucleus on its own. All right, and you know the reasons for instability. Now what we are going to do is, this unstable nucleus itself, even the stable one you can do, but it doesn't happen on its own. You have to do something. We have to start the reaction. Rest it will do it on its own. So the one that an external force or external cause is required, that is non-spontaneous nuclear process. Okay, so that's what we are going to learn. Non-spontaneous nuclear process. Basically, in this, you're going to learn about fission and fusion. But before we reach that, we have to learn certain other things. One is mass defect. Mass defect. Okay, mass defect. We have learned that nucleus is made up of protons and neutrons, which are the nucleons. But the sum of the masses of protons and neutrons, okay, is not equal to the mass of the nucleus. For example, assume that, assume that you have got, say, helium nucleus. Remember, we are going to talk about only nucleuses, no outside electrons. So helium nucleus has 2 protons, 2 neutrons, so mass number is 4. This is so this nucleus has a mass. Also, or I could write 2 protons, 2 neutrons. This is helium nucleus. Now, then you can have individual masses of isolated neutrons. This is one entity, one unit. Now this is what each of them are separated. Okay, separated nucleons. This is nucleus. Now, theoretically speaking, sum of these 4 should be equal to the mass of this one. All right, because this is made only of 2 protons and 2 neutrons. So when you actually find the mass of these individual protons and neutrons, that sum should be equal to the mass of the nucleus. But in practical, this is not like that. In actual, this is not like that. We see that mass of this one is smaller than the combined mass of this. Mass of this is smaller than the combined mass of this, which means when they join to form a tight smaller nuclei, it loses some of their masses. The difference in the mass is called mass defect. Okay, mass defect is equal to actual mass of the nucleus. Let that be delta M. Okay, delta M minus sum of masses of individual or isolated or separated nucleons. What are nucleons, Sanjida? What are nucleons? No, which is bigger? Which is bigger? This is bigger, right? So you can put sum of the masses of the individual nucleons minus mass of nucleus. Okay. So this is mass defect. So what is mass defect? Mass defect delta M is equal to masses of the individual nucleons or sum of the masses of all nucleons minus mass of the nucleus. Now, why? This is explained by Einstein that when the nucleons join together, when these join together, some of the energy is released, and that released energy is affected as a reduction in the mass according to the equation E is equal to mc squared. Okay, that means isolated nucleons have more potential energy, nuclear potential energy. And when joined, when they combine to form, some of the potential energy is released. When they join to form a nucleus, some of this potential energy is released. Okay, this potential energy is called binding energy. Okay, so that is the next one, binding energy. Binding energy could be understood in different ways. Number one, it is the amount of energy released when nucleons join to form a nucleus. Okay, this is the one way of understanding amount of energy released when nucleons join to form a nucleus. Okay. So now here I told you there is a mass defect. Every nucleus will have a mass defect. That means the mass of the nuclei is less than the individual masses. So this mass defect or this difference in the mass, that amount when you convert it to energy using E is equal to mc square, that is exactly same as the amount of energy released. All right. So that's the second way of understanding binding energy. It is the energy equivalent. Energy equal to or equivalent to mass defect. Okay, E is equal to or binding energy, we write by the equation EB, binding energy EB. So binding energy is equal to delta M into C square. Have you understood so far? So what is binding and what is the mass defect? Difference in the masses, sum of the mass of the individual nuclei. That means when the nucleons are separate, their combined mass is bigger than the actual mass of the nucleus. The difference, they are very, very tiny. This difference in the masses is mass defect. And that mass defect, when you convert into energy using E is equal to mc square, what the energy that you get is binding energy. And another way of understanding this is that this is the exact same amount of energy, potential energy released when nucleons come together to join. Now, third way of understanding is in another way. Assume that, so when this happens, when they join, when these nucleons join to join, okay, I'll write like this. So, say you've got the nucleus. Okay, this is the nucleus. This is isolated particles, nucleons of helium. Now, when they combine together to form helium, what happened? Energy is released. So if you have a nucleus at the moment and if you want to separate into isolated ones, what happens? Is energy released or should you put in more energy? Huh? When they come together and join in this process, energy is given out. That means they already give out energy. This has less energy. This has less potential energy. This one has more potential energy. So this excess potential energy, it has already given out. Energy gone. That energy is the binding energy. Now you have this nucleus, you want to separate them. Should you supply energy or will you get energy out? You have to do the opposite supply. Sanjita understood? Sanjita understood?
Yes.
So that means, so this much, how much energy released, that is what you call binding energy. Binding energy is released. Similarly, if you have got a nucleus and if you want to separate, the same amount of binding energy has to be supplied. All right? When they join to form this one, the difference in the extra energy is released and that amount is binding energy. Similarly, if you have got a nucleus and if you want to separate them, the same amount of energy is released. So that is a third way of understanding. Binding energy, EB, this is the most common definition. Okay, most common definition is the amount of energy needed to separate all nucleons, protons and neutrons from the nucleus. Okay, you have got a tight nucleus. If you want to separate them, you have to do a lot of work. You have to supply energy. Okay, amount of energy needed or work, energy or work needed. You can use any one of that term to separate them. Okay, please try to understand how a visual picture about what is binding energy. Okay, that means you think they're all sticking together. So if you want to remove one, separate one, you have to apply a force against that sticking force. Which is that sticking force actually? Nuclear force. Nuclear force is holding them together. So if you want to separate them, you have to do work against that nuclear force to separate them. So how much work you have to do, that is also called binding energy. This much understood?
Yes, Miss.
So in mass units, now you need to have a good understanding of the mass units that we have used in here. Normally the mass unit is kilogram. All right. Another mass unit, especially whenever you do this calculation, since these masses are too tiny, too small compared to the kilogram, then the common unit is this is the SI unit. SI unit is kilogram. Another common unit is atomic mass unit, which is U, unified atomic mass. 1 U is equal to how many kilogram? This you have to remember. Okay, 1 U is equal to 1.6605 times 10 to the power of negative 27 kilogram. Okay, this conversion is given. It will be given, but for the time being, you memorize. Now, this mass is almost equal to the mass of a proton. That is why this one. Another common because since this one has too many 20 10 to the power negatives and all, so this is not a very convenient unit for scientists to use. So what do they do is that they either put it in U, or third one is MeV per C square. Okay, this is another one. This obtained from the formula E is equal to MC square. If the energy is in MeV, then C is equal, so M is equal to E by C square. Okay, a common multiple choice question is convert 1 MeV per C square to kilogram. You know how to convert? You know how to convert? 1 into mega means to the power of 6. EV means 1.6 into 10 to the power of negative 19 divided by 3 times 10 to the power of 8 square. This many kilogram. Okay, learn this conversion. And this should come around 1.77 into 10 to the power of negative 30 kilogram. Okay, so the questions will be either in kilogram or in U or in MeV per C square. All these are mass units. Whatever units comes, you should know how to convert to kilogram. SI unit is kilogram. If you want to get it in joules, mass must be in kilogram. Okay. Now, there are many questions in your textbook about calculation of binding energy. Okay, calculation of binding energy. Now, the next topic that we need to do is binding energy per nucleon. Binding energy per nucleon, which we write as EBN, subscript N. Binding energy per nucleon. Okay, what does that mean? As the name says, binding energy per nucleon is equal to binding energy divided by number of nucleons. What is the number of nucleons called? Number of nucleons. What is it commonly called as? Which number? No, what's the name? Number of nucleons is otherwise called mass number. Mass number. Okay. Binding energy per nucleon is equal to binding energy per or divided by mass. So what did we do? We did mass units. We did binding energy per nucleon. This is very, very important. Binding energy per nucleon is a very important concept because it tells you, okay, what is actually binding energy? Assume that oxygen has how many nucleons? 16 nucleons. Okay, so sum of protons and neutrons is 16 nucleus. So that binding energy of 16 nucleus divided by 16 will be binding energy per nucleon of high oxygen. Okay, so that every nucleon, so in an average, how much energy you have to spend to remove one electron or to remove one proton? That is binding energy per nucleon. So that is more significant other than the binding energy, because a smaller element will have its own binding energy, larger element will have its own binding energy. So you cannot compare the binding energies. But if you compare the energy needed to remove one from this and one from this, that would be a better comparison. That is why we use binding energy per nucleon. Okay, Why this is important? Because it tells you about the stability of atom, stability of nucleus. That means, is it a material eligible for spontaneous nuclear process, or is it an element which is useful for doing fission or fusion? Okay, so to determine all those things, we are using binding energy per nucleon curve. Okay, so let's do that now. Meanwhile, you take down this one, binding energy, sorry, mass units, and this one. Between U and MeV per c square. That is 1 U is equal to 931.5 MeV per c square. That means 1 U of mass, if you convert to energy, you will get 931.5 MeV. Okay, this is the relation between 1 U and MeV per c square. Finished? Okay, so now let us continue with binding energy per nucleon curve. Binding energy per nucleon curve. This means this is a graph of binding energy against mass number. Okay, binding energy against mass number. So here we have EBN and here you have mass number here. Okay, the actual graph, I'll send you a picture. This one. Okay, so this is the actual picture. All right. So you got it. All of you got this picture. Have a good look at that picture. This tells a lot about Why certain materials will undergo fission easily, why others fusion. So just have a good look at that. See, look here, in this one, atomic number 0 to atomic number 250 are marked. So this may be 50, this may be 100, 150, 200, 250. Okay. What is the, the highest one will be much more, okay, bigger than that. But common elements are included in this. And here we have EBN, and it starts from 0, say 2, 4, 6, 8, 10. Okay, up to 10 only, 0 to 10 only. And you see hydrogen is having somewhere between 0 and 2, somewhere here. This is hydrogen 2. Hydrogen 2 is what? Deuterium. Hydrogen 3 is here. You can see tritium. Then comes lithium is little bit below 6. Okay. Then in between, this is hydrogen, this is hydrogen, this is lithium. But you have got helium in between. But helium is much above this one. Here is helium. Okay. 1, 2, 3. Atomic number 3. Then you have got so many other, and like this, the graph goes like this. The graph goes like this. Then there are so many changes, and you see that the peak is for iron, which is 56. This number is 56, and this is iron. That has the highest binding energy per nucleon, and up to 30. Yes, somewhere here 30 to 170. 170 is somewhere here. Okay, so like this. Fine. Yes. See, look here. And then it decreases. Here, this is a very, very helpful graph. What does that tell you? Most of the elements between 30 and say 170, right? For them, what is the binding energy per nucleon is here till this much. And look at this. Look at this. See, look here. If you draw a number between 8. So from this one, see, most of the elements with the mass number 30 to 170 have a binding energy almost 8. That means in this range, 8 to 10. Okay, 8, 9 like this. Okay, but 10 is somewhere here, for example. So this is very important. Most of the elements, that means the element with the mass number 1, mass number greater than 30 and mass number less than 170 have almost constant, almost similar or constant binding energy per nucleon, which is around 8 MeV. This is in MeV. Nuclear energies are in MeV. Okay, this is the first observation. Most of the elements, and that is with mass number 30 to 170, have almost constant this range, and it is around 8 MeV. This is the first observation that you get, which means elements below 30 and bigger than 170. Okay, number 2. Elements with atomic number less than 30 and atomic number bigger than 170 have smaller binding energy per nucleon. So why that is important? Because smaller binding energy means what? You need to supply only less energy to separate. That means they can be easily separated. That means they are unstable. Okay, that is the sequence. Less binding energy per nucleon indicates that with little energy, nucleons can be separated. That means they can be easily separated, which means can be easily separated, which means less stable. Okay, so this is the direct consequence. Less binding energy means less stable. So which are the elements less stable? Elements with the mass number less than 30 and elements with mass number greater than 170. So these are two sections which are less stable. Okay, why we need a less stable one? Because they are the ones that we can easily manipulate with. We can do some experiment with stable elements. You have to supply a lot of energy to separate them. So we are not able to touch those stable. We are able to do with this one, and so we have triggered processes using this one. Now, which is the stable, the most stable element is this one. This is the third observation. Third observation, iron. Okay, with binding energy per nucleon around 8.7 MeV. 8.75 MeV is the most stable nuclei. Okay, so this, remember, these are the observations that you can conclude from this binding energy per nucleon curve. Sanjita, understood?
Yes, miss.
Okay, so now I told you there are two groups, less than 30, more than 170. Okay, so that means if it is less than 30, you can do fusion, or for example, let me put it in this way. Another important thumb rule for triggered nuclear process, which are fission and fusion. This is the principle for fission and fusion. These are the triggered nuclear processes. The golden rule is, okay, see, look here. Here what do you have? A low binding energy. Here you have got another low binding energy. When two hydrogen nuclei join together, what do you get? Helium. Helium has bigger binding energy. Okay, so if low binding energy, if you are able to convert low binding energy to a bigger binding energy, the difference in the energy is released. That is a golden rule for both. If a nucleus is converted to, or if a nuclei of lower binding energy is converted to higher binding energy, then energy is released. This is the golden rule for this one. Okay, what is the rule? If you are able to convert these are lower binding energy elements. if you are able to convert these to a higher binding energy, then this will release lot of energy to you that you can use it to create electricity, like in the reactor or bomb, right? So this is the gold rule. If, please memorize this one, if low binding energy nucleus, somehow if you are able to convert to higher one by joining or by splitting somehow, you will get lot of energy out. Okay, that means nuclear energy. Nuclear force is the strongest force, therefore the energy contained inside the nucleus is also the largest amount. So if you somehow convert this low binding energy elements to high binding energy, lot of energy will be released. Similarly, here too, low binding energy, here the common one is uranium. Uranium has atomic number 245, sorry, 235, 200 here, okay, somewhere here, right? Here you have got uranium. If you are able to, now uranium is a large nucleus. Here, this is very tiny, small, here and all, it's reasonably big. The size of the nucleus will increase, and when it comes here, it is the massive. So here, what you are doing, so we have got two. So in fusion, what is happening? Two low binding energy nuclei are joined to helium. Helium has higher binding energy. In fission, what do we have? Again, this is uranium. This is uranium. Uranium is split. When uranium is split, you will get barium and krypton, which are in this range. Again, low binding energy to bigger binding energy. Then the energy is released. Okay. So this, what happens here with these is fusion. And what happens with this is fission. Okay, so in fusion, what happens? Two low binding energy nuclei are joined to form helium, which has got high binding energy. In fission is for bigger elements. Here what happens? Again, a low binding energy nuclei is split into two barium and krypton. There are many variations. Okay, barium and krypton, which have high binding energy per nucleon. In this process also, energy is released. To understand this, okay, we started with binding energy. Okay, so that means here what happens in fission? Fission means splitting. Heavy, large nucleus are easy to split. Okay, so when you split this one, you will that will break down to two elements which will fall in this range. So somehow your aim is to bring elements to this range after either splitting or joining. Okay, so this is the thumb rule. If a nucleus of low binding energy is converted to higher binding energy, the nuclear energy is a very huge amount is released. So that is how we got two processes. One is fission, other is fusion. Fission is done with, fission means splitting. Big things are easy to split. Therefore, uranium can be easily split to form barium and krypton, releasing large amount of energy. Similarly, hydrogen is having low binding energy. When you join them, okay, when you join them, you get a bigger element, a helium, which also has higher binding energy or binding energy per nucleon. Is this understood? Now let's learn in detail about fission, then later fusion. Okay, fission you might have learned already, so I can really go fast. Nuclear, you have learned about fission in biology probably. Cell division, fission. Nuclear fission. Hello. 15 മിനിറ്റ് 7:50. Okay, nuclear fission. Okay, fission means splitting, which is easy to split, big or small, bigger elements, big nuclei. That's a clue. Big nuclei you split, you will get two smaller which has high binding energy. So what is nuclear fission? When a heavy nucleus is split. And how is that? How do we split? How do we actually split? It's rather easy. Why? Simply hit it with a slow neutron. Okay, is split by a slow neutron barrier. There are many variations. One example only I'm giving. Okay, two smaller nuclei with high binding energy are released. Okay, two smaller nuclei with high binding energy, then what? Okay, two or three neutrons and large amount of energy. This is nuclear fission, right? And the simplest example, one of this example you have to memorize. The simplest example will be uranium 92 to 35. This is the fissionable material. You are simply hitting it with a slow neutron. Slow neutron, simply write neutron, no charge, one mass. What initially happens is that this neutron gets inside the nucleus of this one. That means you get a combined one with 92 to 36. This is an intermediate combined one, very, very unstable. So this quickly breaks down to barium plus krypton plus 3 neutrons, 2 or 3 neutrons plus large amount of energy. Okay, so at least this one you have to memorize. Okay, at least one equation. I will put two more equations in the group. You can copy them down. These variations are also possible. All right. Okay. Now, yes. So this is the nuclear fission. Now, how much energy is released? That is called Q value. Okay, energy release. This energy released is called actually Q value is found how? The mass difference. That means sum of the masses of this minus sum of the masses of this into C square. That means mass of uranium plus mass of neutron. This is the reactant, right? Minus mass of barium plus mass of krypton plus 3 into mass of neutron. Okay, now this is the difference in the mass. This times C square. This is how you find how much of energy is released. Okay, how much of energy is released. Now this is also called Q value. Now this one, okay, now let's learn about a nuclear reactor. How does a nuclear reactor work? Before we learn about a nuclear reactor, you should know about a chain reaction. What is a chain reaction? Because what happens in a nuclear power plant and nuclear bomb are exactly same thing. Fission of uranium. In a nuclear bomb or in a nuclear reactor, what basically happens is same thing, which is splitting of uranium. Okay, but there is a major difference. That difference can be understood if you know about chain reaction. What is chain reaction? Assume that you have got a nucleus or you have got a sample of uranium. Okay, this is that much. This is hit with a neutron. Then what happens? This one splits down to barium, krypton plus 3 neutrons plus lot of energy. Okay, now what do these 3 neutrons do? That is important. These 3 neutrons, okay, they can undergo fission with another 3 uranium atoms after doing some manipulation with them. They are also capable of hitting 3 more nuclei. Then what happens? The same thing gets repeated. This one breaks down to barium, krypton, and 3 more neutrons again, plus energy. This also will break down to barium, krypton, and 3 neutrons. Neutron. This also can break down to barium, krypton, and 3 more neutron. Now each of these 3 more neutron are capable of hitting other uraniums. So like that, this continues until all uranium atoms are split. Okay, so chain reaction means you are triggering only once in the beginning. Then that will produce 3 more similar neutrons. But there is a problem that we will learn when we learn about nuclear reactor. Those 3 neutrons can go and hit other uranium atoms, which will again produce 3 more neutrons, 2 or 3 more neutrons. That means once you start, it keep on splitting the uranium atoms present in that sample. If you got 100 uranium atoms in a sample, if you trigger only once in the beginning, This happens quickly until all the 100 uranium atoms are split. If you don't control them, it will go indefinitely, or it will go, all these uranium atoms will get split in a fraction of a second. The danger in that? The danger in that is that every time a nucleus is split, energy is produced, energy is produced. And this energy, since lot of energy is coming in a small period of time, we do not have resources or tanks to store that energy. We don't have any ways to store that energy, because before we could even think of this energy coming, they will be exploded. This happens in a very tiny time. Few microseconds, nanoseconds, one uranium gets split. So what is the consequence is that large amount of energy is coming in a small period of time, which is, that time is too insufficient for us to do any sort of storage. So it will explode. All the energy will come out quickly in a fraction of a second, which is what you call as nuclear bomb, nuclear explosion. Okay, so this is chain reaction. So next class we will learn how to control them, because uncontrolled chain reaction is of no use to us except in making bombs. So this is actually what happens in uncontrolled, in bombs, where uncontrolled chain reaction happens. If you can able to control it, then it is very good. You can use it because the energy is coming in a smaller rate or slowly, so that we humans can handle and store that energy, and we can utilize for different purposes. So that is how a nuclear reactor works. Okay, so we'll learn about the nuclear reactor in the next class. Any doubts so far? Okay, let me give you the notes now. I want your notes today itself, or not today, maybe tomorrow morning, if possible today itself. Using this is only very rough note or very brief note. You make a detailed note and give me today or latest by tomorrow.
Miss, Miss, for next week, the 2 classes, can you switch it to this week? Because next week I'll be unavailable from Sunday till Thursday.